Hi, this is Alex from devstories.eu. SunPy, Solar Data Analysis, Episode 2 of 12. A massive two-dimensional array of numbers representing solar pixels is completely useless if you do not know the instrument that captured it, the wavelength, or the exact date. To do any real science, those pixels must stay permanently fused to their context. This is the exact problem solved by the map abstraction. A very common mistake is assuming that a sunpy map is just a convenience wrapper for making plots. It is not. While it certainly can draw images, at its core, a map is a coordinate-aware data container. It acts as the central glue that prevents you from losing your metadata when you manipulate the underlying pixels. Let us look at how this works in practice. Suppose you have downloaded a FITS file containing an AIA observation at 171 angstroms. FITS is the standard file format for astronomical data, and it stores both the raw image array and a header full of observation details. To bring this into your environment, you pass your file path into the sunpy.map.Map function. This function actually acts as a factory. It reads the file, automatically detects which instrument took the image, and returns a specialized map object. We will just call our new object myMap. Once you have your map, the first primary component to explore is the metadata. Solar observatories pack a tremendous amount of detail into the FITS header, and SunPy extracts all of this into an attribute called mymap.meta. This attribute behaves exactly like a standard Python dictionary. This means you can programmatically read specific keys to drive your analysis. For example, if your script needs to extract the exact observation date, you just access the date key directly from the meta dictionary. SunPy also normalizes many of these header keys, smoothing out the differences between how various solar instruments name their metadata fields. Now, the second piece of this is the image itself. Here is the key insight. The map object does not try to reinvent how numerical arrays work. The actual pixel data is stored in an attribute called mymap.data, and this is nothing more than a standard two-dimensional NumPy array. Because it is just NumPy, you do not need to learn a new syntax to do your mathematical work. If you want to find the absolute brightest spot in your AIA image, you extract mymap.data and run a standard maximum function over it. You get your raw pixel value instantly. By keeping the meta dictionary and the data array wrapped up tightly together inside a single map object, SunPy ensures that your physical units and instrument context are never separated from the raw numbers. It provides a single boundary around everything that makes those pixels meaningful. The real power of the map abstraction is not that it draws the sun, but that it forces the raw image array and the observational context to travel through your codebase as a single, inseparable unit. That's all for this one. Thanks for listening, and keep building.